Hello! We will discuss the role of the objective function in a linear program from the geometric point of view. We start with an example. Consider the following linear program. Notice that we have inequality constraints rather than equality constraints. Also, there are technically 5 constraints here, including the non-negativity constraints. Recall that each of these inequality constraints defines a hash space, and the feasible region is the intersection of all these hash spaces. The feasible region for our example is illustrated here. The extreme points are also labeled. We now consider the objective function, and let z represent the objective value. So z is equal to x1 plus x2. Now thinking of z as a constant term, this represents a line. Each value of z gives a different line, all of which are parallel to each other. And here are the lines for z is equal to 0, 1, 2, and 3. Here is an observation. Any point, feasible or not, that is on the line z equal to x1 plus x2 has objective value z. So as long as z equals to x1 plus x2 intersects some point in the feasible region, then a feasible solution achieves the value of z. So for our linear program, its maximum value must be at least z. In our diagram here, when z is equal to 3, the line intersects some points of the feasible region, like 0, 3. And all these points have objective value 3. We now look at the vector c, which is 1, 1 in this case. So how is this vector related to the lines? It is the norm of these lines, which is the direction that is perpendicular to these lines. Now can you find a relation between the vector c and the movement of the lines as z is increasing? We see that increasing the value of z is the same as pulling the line in the direction of c. The further you pull in the direction of c, the higher the value of z. Now in our LP, we want to maximize z. So what we want to do then is, we will pull the line as far as possible while intersecting the feasible region. The last point of intersection then is optimal. In this example, optimum is achieved at z is equal to 6, and the optimal solution is 4, 2, with optimal value 6. We note that this is an extreme point. Now, it might make sense that, in general, when we pull a line as far as possible, we will end up with a corner point of this polyhedron. But there are cases where we might not end with just a point. Suppose we change the objective function in this example so that c is 1, 0. That means that z is equal to x1. This means that we are pulling a vertical line to the right as far as possible. In this case, we end with z equals to 4, which intersects a segment, and anything beyond that, there is no intersection. So then, every point on the line segment from 4, 0 to 4, 2 is optimal, with optimal value 4. More generally, when you pull the line as far as possible, the last place where it intersects the feasible region must be at the boundary of the polyhedron. If there is any intersection in the interior of the polyhedron, this means that there is an open space around it that is still in the polyhedron, so we can still move in any direction and improve the solution. So the key thing to take away from here is that if there is an optimal solution, then it must be on the boundary of the polyhedron. Now in R2, the boundary of a polyhedron is formed by points and lines. But what about higher dimensions? Let's have a look at an example of a cube in R3. Say it is defined by all three variables ranging from 0 to 1. The objective function would take the form of z equals to c1x1 plus c2x2 plus c3x3, which is a plane with normal vector c, which is c1, c2, c3. So maximizing c transpose x means pulling the plane z equals to c transpose x as far as possible in the direction of c. So what could optimal solutions look like? We might have c equals to 1, 1, 1, where we pull the plane in all three axes, and this will end with a point, which is going to be 1, 1, 1. If we have the objective 1, 1, 0, we are pulling the plane in the direction of x1 and x2, and we will end with a line. So the optimal solution would be a line segment from 1, 1, 0 to 1, 1, 1. If c is 1, 0, 0, then we are only pulling towards the direction of the x1 axis, and it will end at a plane, and everything in this square is optimal. More generally in Rn, we are pulling the hyperplane z equals to c transpose x of dimension n-1 in the direction of c. At optimum, the intersection must be at the boundary, which could range from a zero-dimensional point to an n-1 dimensional hyperplane. Note that there is a trivial case where the entire feasible region is optimal. We will leave this as an exercise. We now look at how this is related to simplex. Recall how simplex works. Simplex goes from basis to basis, trying to improve the objective value at each step. Also recall that each basis corresponds to an extreme point of the feasible region. So then geometrically, simplex is going from one extreme point to a neighboring extreme point. In our example here, simplex could go from 0, 0 to 4, 0 to 4, 2. Or in the case of a cube, simplex might go from 0, 0, 0 to 1, 0, 0 to 1, 1, 0 to 1, 1, 1. Now in each iteration, we move our basic feasible solution in a certain direction. For example, when we moved from 0, 0 to 4, 0, we're moving in the direction of 1, 0. So now, how does this direction compare to the direction of the objective function c? Comparing with the direction of the objective, these two directions are on the same side of the line. We will leave the details of this as an exercise. So then, moving towards the chosen direction in simplex improves the objective value. Let's take a look at a numerical example. Say I have the LP here. Our starting solution is x equals to 0 to 3. Our entering variable is x1 and our leaving variable is x2. Going through the process, we will set x1 is equal to t, then x2 is 2 minus t, and x3 is 3 minus t. Our new solution would be x bar, which is 0 to 3 plus t times 1 minus 1 minus 1. So we are moving the solution in this direction, the direction of 1 minus 1 minus 1. If we take a rough sketch of this, we have a plane where we're pulling towards the direction of 1, 0, 0, and x moves in the direction of 1 minus 1 minus 1. Both of these vectors are on the same side of the plane, so moving x in this direction would improve the objective value. Now simplex will only deal with basic feasible solutions, which are extreme points. And also, simplex will find an optimal solution if one exists. So combining these two facts, we can come up with this theorem. For a linear program in standard equality form, if there exists an optimal solution, then there exists an optimal solution that is an extreme point of the feasible region. Now, this does not mean that all optimal solutions are extreme points. As we have seen, some optimal solutions are just on the boundary, but not necessarily extreme points. But we know that at least one of them will be an extreme point. Also note that this is not always true if the LP is not in standard equality form. As an exercise, try to find one such example. And that concludes our discussion on the geometry of objective functions. We will discuss this topic and the geometry of optimal solutions in more detail at the end of Module 3.